Multivariable calculus, we are back in 15.7, section 15.7, our first day, picking back up with a solid region of type 2 where the boundaries are with x bounded between two curves. And that means that the domain that we have a double integral over will be over the y-z axes. So rework example 2, but this time get this problem as a type 2 region. Now we might not think of this as a type 2 region at first, but look, we could say x is bounded between two curves. You can say, now wait a minute, as you drew this little red segment here, you can think, well, what in the world are these boundaries? Well, remember that really we have this parabolic cylinder that's rising up. So we had y equals x squared. If we wanted to solve for x, x would be plus or minus radical y. So right here we'd have x would equal the positive radical y. Over here on that left this far region off in that negative region where x would have a boundary, that would be negative radical y. So that's where we're going. And we could actually begin very, very quickly then to say, look, we're going to go between negative radical y and positive radical y. And of course, our integrand would be z, and we'd have dx. And then very, very, very importantly, we'll have to talk about the domain that we're going to have our double integral over. Well, it won't take you too long to see right here that your antiderivative would be in x times z, and, we'll be integrating from negative radical y up to positive radical y. And as we work that out with the fundamental theorem, you could see we could pull our z out. We'd have a radical y minus this negative radical y, and that's going to become a 2 radical y. So our integrand actually is going to be a 2z radical y. But as we're working this out, the big question is, what is d? Well, as we saw right here, if your boundaries are in regard to x, remember that your region D is going to get projected over the axis that doesn't have that variable x in it. In other words, it will be on the zy axis. And again, you can envision a shadow, or you can envision like a garbage wall smashing that in there, and you'd say, well, what would that region look like? Well, imagine that we've got this garbage wall smashing in even from both sides, and it's going to smush this in on the zy axis. I hope you could see that it's actually going to look like this triangle right here. So our region D, what we're going to have is on the zy axis. It's going to look something just like so. And of course, this is coming from the y plus z equals 4, or the z equals 4 minus y. And right here, you could say, well, if that's region D, and we can make that green like we had earlier, this is going back to our previous section. It's kind of like our z is like our y, and our y is like our x. But if I just drew in vertical bars here, you could see that our z would always be contained with an upper and a lower boundary. And I'm going to really make use of that real quickly. We could say, look, we could say that our z would be going from 0, that came from the z equals 0 component, all the way up here we'd have a 4 minus y, and we'd want all such vertical bars from y equals 0 to y equals 4. And, once you have that worked out, honestly, you could just get help from your TI-89 right here. Of course, you could work it out by hand just as well. But thank goodness you're going to get the same answer that you got for example 2. As well you should. Now, we're doing this primarily to show you that you can definitely work these problems out from multiple perspectives. I think everyone would agree quickly that usually one type of region will be way more accessible and will be easier for students to think about, but you can always look at it from a different perspective. Here's one last region, a type 3 region, is where your y's are bounded between two curves. You could see once again that perhaps your y values will always be greater than and less than two curves, which we'd like to write as curves involving just x and z. So, as we're working that out, you can see more or less what is happening here. As we venture on, and of course here we go with that region once again, D. Notice that projection, as we look at that projection, you can see that we're actually going to have a projection onto the axis not involving y, the xz axis. Again, kind of like a shadow idea, or imagine a garbage wall smashing that solid into that plane. Last example, I've already drawn a picture to speed this up. They're saying more or less, can you go ahead and get this worked out in regard to a type 3 region? A type 3 region in that you can see that your two curves are primarily described with y equals equations. In other words, you'd have functions involving x and z, really. So we've got a paraboloid. It's a three-dimensional parabola. Again, it can look kind of like a gumdrop, kind of like so in 3D. And when you have y equals x squared plus z, you can see we've graphed that right here. You've got this, paraboloid vertex at, the origin, but it's opening in the y direction, and it's, centered about the y-axis. So then we also have y equals 4, which is this plane right here. So we've got this gumdrop, so to speak, sliced off with y equals 4. And that's going to be your solid. Look at this red bar right here. I'm going to redraw it, make it a little bit thicker. Your gumdrop here has a definite starting biggest point right here, and then touching that actual paraboloid. Your y values are always between those two. So as we're working this integral out, we could say, well, look, I'm going to have a y boundary. The biggest it will ever be is 4, and the smallest we're going to have is an x squared plus z squared. And, of course, in here we'll have x squared plus z squared for our integrand. And, right now we could even work this thing out. We could say, hey, as we get this thing going, we could say we'd have our x squared plus z squared, and then we'd have a y, and we'd be going from x squared plus z squared all the way up to 4. And as we work this thing out, I think you can see rather quickly that we'd have a 4 minus, and then we'd have our x squared plus z squared. And, right now, I think as you're looking at this, maybe perhaps as we're going into this, domain D, I've already drawn this in right here. You can see that the shadow, we get a circle with this paraboloid when y is equal to 4. When y equals 4, this becomes 4 equals x squared plus z squared. That's really the intersection that you'd get. And a shadow, as we'd project this down, would be a circle. So, as we're looking at region D on an XZ axis, you could see that we're going out 4 steps. We're really getting a circular region. And in fact, if we smushed that gumdrop down with a collapsing garbage wall, so to speak, we'd get this circle. And guys, as we see circles, I hope you are thinking about polar coordinates. Do you have to use them? No, but oh my goodness, do they make life easier. Look, we'd have x squared plus z squared equals r squared in general for a polar type of coordinate. We'd have x is equal to r cosine of theta, z, which is kind of what we traditionally would see in y, would be z equals r sine of theta. And wow, we're looking at this entire region here. Any point x comma z would have a radius, of course. So wow, as we begin to look through this, we could immediately see that x squared plus z squared is r squared. So this is the square root of r squared. This would be 4 minus, well, x squared plus z squared is r squared. And dA, well, we could have an r dr d theta. And our r boundaries, well, if you look in green there, we go from 0 all the way out to 4. Our theta boundaries, well, we're going to go from 0 all the way out to 2 pi. And it's not going to take you too long. This square root of r squared is just an r. So, wow, we could, finish this up hopefully pretty quickly. We'll have really an r squared times a 4 minus r squared right here. And just as we're, cleaning this up. So we have a 4r squared minus r to the 4th. And then we just have to get this thing cleaned up. Taking our antiderivative, we'll get 4/3 r cubed minus r to the 5th over 5. And, then we can, of course, just get this thing finished up. And, as we're doing that, of course, wow, as we're looking at this thing right here, we could try to get it cleaned up a little bit, plugging in a 4 and getting that to work out. By the way, pardon me, I just realized I made a little mistake. Maybe you've caught it too. R squared, if that's equal to 4, that means r is equal to 2. I am so very sorry. Let's fix that, please. It's really just a quick fix here. I was using our r squared instead of an r boundary. So, oops, let's just clean that up. This is going to be a 2. So really, we're going to have, this, aren't we? We're going to have this, situation right here. X squared plus z squared equals 4. That's really like x squared plus z squared equals 2 squared. So sorry about that. When we plug in a 2 right here, 2 cubed is 8. 8 times 4 is 32. That's 32 over 3. 2 to the 5th is 32. That's 32 over 5. And, wow, we can real quickly just factor out a 32 and, get a common denominator. That's 5/15 minus 3/15. That's 2/15 times a 32. So that's 64/15 that we've got right here. And then finishing up, you should get